My name is Randy Noland, and I'm Vice President of Business Development and Director of Machine Control at Carlson Software. I'd like to thank the Oregon Department of Transportation for asking me to speak at the Design to Dozer seminar. I think it's a fantastic program and hopefully can participate every year when they have one of these events. My topic is unique machine control applications. And what we'll discuss to begin with are 3D drilling, which is not unlike pile driving, and how we can set that up and take advantage of machine control technology. Also compaction, and the example that I'll give will be landfill compaction, but soil compaction, asphalt, etc. It's not unlike those. The applications are very similar. And what I'd like to say at this point is that really what we're talking about with 3D machine control is an array of sensors that monitor the articulation of a machine. So if it's a drill, compactor, or any of the other machines that can take advantage of this technology, basically we're just monitoring their articulation, bringing that data in together into a computer, basically a ruggedized control box, and then the software or application software provides the necessary data and feedback to the operator. So it's a bit of a simplification of what's going on here, but it helps kind of explain how we are able and open the mind as to what we can address with this technology. We'll also touch on data flow and the design build life cycle and how important that is to these machines, and also connectivity and analysis, taking machines, making them part of a connected site, and sending data to them, logging and streaming data back into a central location, and then analyzing that for various benefits we'll discuss. Now, many of us are familiar with the work that dozers and graders and scrapers and excavators do, and perhaps the role that machine control technology plays in those types of equipment. But depending on the terrain or depending on the application, the drill or drilling a lot of time precedes all of these machines, and 3D machine control can benefit that application as well. For example, if I'm on a construction site with a lot of rock or I'm building a highway, the drill is used to, of course, drill blast holes per an engineer's design, so we can blast, move the rock, and come back, blast again, move the rock until we can achieve our design, and then bring in the other machines to be productive. So 3D drilling, very good candidate for machine control technology and for the blast holes. Now, all of the design holes for blasting are, they are designed with precision by an engineer, and these blast holes are in a set grid. They are angled and parallel and angled together so that the blast is designed for maximum benefit. And some of the reasons for this is to eliminate fly rock, also to make sure that the fragmentation is really, you get the desired fragmentation. If you blast inappropriately or not according to design, which can occur by inaccurate drilling or the blast hole angles are not exactly parallel, well, you affect the entire downstream process. The rocks are too big, the material's too big, it has to be broken up. You stress the wheel loaders or track loaders and trucks that move this material away. So these are some of the desired benefits, and 3D machine control can enhance all of these. The other thing is that you're eliminating a person at the work face. You'll notice in the picture to the left, one drill is actually drilling using 3D machine control, and the other drill is having the drill holes marked with paint by the operator. So being able to just use a pattern on the screen, navigate to the hole, and drill, eliminates people or work persons at the work phase. So 3D drilling, if the more accurate that it's done, the more positive and productive all of the downstream processes will be, from fragmentation to moving the material. Here is a video I shot in May of 2010, and this will show you a drill navigating. You can see the heading there, and we've got a 3D design for the drill holes on the screen, and that can be loaded into the drill so the operator can simply use that pattern, or grids and drill patterns can be designed in the field by the operator. Here we see the operator has selected a hole. He has navigated to position himself to the hole, and now he's placing the drill more accurately on top of where the design says to begin drilling. Once the drill is placed, then the software can monitor the depth through with the encoders. So there are axial sensors on the body, on the mast. There's RTK GPS on top of the mast. There's heading that help you, again, all the sensors coming together, monitoring articulation, and then the application software interacts with the operator. Here they're placing tires and canopy across the blast area to help reduce fly rock. They're removing all of the machines, clearing the area for the blast. The all clear signal is given, and the machines will go in, break up if they need to, and remove this material. Let's now take a look at compaction and how 3D machine control can be applied to monitor a machine, providing an application-centric information for compaction. Here on the left we see a landfill, and one of the first things that you can determine is that if I am moving a machine back and forth across material, be it trash or soil or whatever, I need to be able to measure how well I am compacting, and I want to reach optimal compaction. If I don't compact enough, then I'm wasting space and the material is either unstable, or in the case of a landfill, leaving too much airspace and I'm not making the best use of my space. Or if I overcompact, I'm wasting time, machine wear, fuel, etc. And of course, that costs money. So first and foremost, we want to optimize compaction. And we can do this in two ways. One is deflection, and that simply means that we're measuring the vertical difference, how far down we're moving with each pass of the machine. And we're basically using RTK GPS, GNSS, to tell us how well we're pressing down. And once we've reached a point of diminishing returns, then we know and we can move on. The other method is through pass counts. And basically pass counts are a good general rule to say, based on the material or the waste stream, I need to make 3 passes or 5 passes across every part of the material to reach optimum compaction. Well, it's not real easy to know everywhere you've been, so it can be fairly unproductive and a fair amount of guesswork. So if I roll over a particular area once, twice, 3 times, I need to know exactly where I've been. So application software will color the screen with each pass, measuring and coloring exactly the size of the machine's compaction footprint. So this way the operator knows exactly where and how they've compacted or where the passes have been. Another method is through intelligent sensors, and this actually measures the sine wave basically, or the vibration amount that's being returned from the machine. So as this reduces, as the vibration or the back energy is reported, then I can measure my compaction or density, or have an idea where I'm at with intelligent sensors. Another feature that the technology offers is dynamic data exchange, and by this we mean if I have, let's say on a landfill, compactor A and I have compactor B, and they need to make 3 pass counts to reach optimal compaction. Well, every time compactor A goes over a particular area, that would be 1 pass count, 2 to go. But with dynamic data exchange requiring a wireless infrastructure, mesh radios for example, then this data is immediately updated in compactor B, so that if they approach exactly the same area, they will have an up-to-date pass count so that the 2 machines can productively work in tandem. The other thing that they require that machine control contributes to is managing slopes. Even in a landfill where it's trash, we need to make sure that the slopes are managed correctly and that the slopes don't fail and that the machines are not working against too steep a slope, etc. So the technology lets us know how to build a 2-to-1 slope, for example. This also helps us manage water leachate, which is contaminated water or fluid. So managing slopes is another advantage of the technology in compaction applications. GPS landfill management offers a lot of features and benefits. One is having real-time pass counts. So the operator knows how many times they've been over any area in real time. This saves fuel, this saves wear and tear on the machine, and it also saves the amount of passes and production and time it takes to reach optimum compaction.
This their compaction rate is tremendous.
Is that right?
I think the last compaction rate we got was 18.4, something like that. Where before is down to like 13-14%.
Wow.
On the rig, it'll tell you when you're too close to the other compactors. So I let you know when you're getting too close to them. You can move your screen around, you can make your touch screen. Then have a little dot, he's done one out of my side now. Tell you where the other compactors are.
And they can see you as well.
Right. There's one. Thickness. We change it to a 2-foot lift.
And some of the other benefits where we've saved money with the GPS is not directly related to slopes and everything, but I can look and see when a piece of equipment started up and how long it sits and idles and how many passes they made. You know, we want them to do 3 or 4 passes and move on. If they're doing 10 or 12 passes, then they're burning more fuel. You know.
Let's discuss the design-build life cycle and the flow of data across the different phases of the design-build process. Now, the machines we've been looking at, of course, are part of the building process, but they're